Hello viewers, so in this video you're going to look at how to answer questions related to related rates. Okay, here number 7 says a cylindrical tank with radius of 5 meters is being filled with water at the rate of 3 meters cubed per minute. Now you should just write that data down as you read it. Okay, so what is this? What does this mean? You see the units, its unit is meters cubed per minute. Its volume, meters cubed is volume, minute is time, so it's change in volume per time. That is your dv dt. How fast is your volume changing with respect to time? Okay, it's given by 3 meters cubed per minute. You write it down like that. Now the question is how fast is this was how fast the volume is changing. Now question is how fast is the height of the water increasing. uh, Schematically, this is what we are looking at. We have a cylinder like this, okay, and then we have the base of the cylinder here and the height. Okay, you have the height there. Now what is the volume of this cylinder? That's where you want to start. You want to start with the formula that relates the volume, the height, and everything that is given here. That is the radius. For the cylinder, that formula is given by V is the same as area of this base, okay, multiplied by height. So you say area of that base, and the base is a circular base, that's pi r squared, area of a circle, okay, multiply by height. Now this is your formula for the volume of this cylinder, okay. Now your question is, don't forget, your question is you are looking for dh dt. This is the question. How fast is the height changing with respect to time? Now you must note this down. If they say how fast is the height increasing, we're going to get a positive answer, because I mean the height is increasing as you put on water here. As we put more water here, the height of that water is going to keep on going up. Okay. Now, knowing that the height of the water is going to keep on going up, we know that the answer here is going to be a positive value. That's how we know it's going to be a positive value. This one, we write a positive 3. We know that the way the volume changes, it's increasing. The volume is increasing as you put on more water in there. Okay, so the first step is to write the formula that relates the 3, and then you identify your constants. Identify your constants. The things that are not changing are constants. Pi and r squared, they are not going to change. Okay, your pi and your r squared, they are not going to change because r is constant. If if this was a cone, the radius will change as height goes up. I mean, cone looks like this, right? And if you fill up water, the radius is going to increase, you see, as you go up. Now we're not looking at the cone, we're looking at the cylinder, and the radius remains constant. So knowing that the radius is constant, we just have to do what? We just have to treat it as a constant. Okay, so we will say we are going to take on this formula the derivative d over dt. Why d over dt? Why are we differentiating this thing with respect to time, whereas there was no time here? We are differentiating to time because our quantities are given with respect to time. 3 meters cubed per minute. How fast? We are looking at time. How fast? How fast? The question says how fast as well. We are looking at time. We are looking at how fast the height is changing with respect to time. Okay, so we're going to look at that. So that's why we're differentiating with respect to time here. Okay, now dv dt is the answer for when you take this your d dt here. You differentiate v with respect to time, you get dv dt. You have v to the power of 1. You see the power of v is 1, so it's just dv dt. It's like you see y. Differentiate y with respect to x. The answer is dy dx. Here is you see v to the power of 1. Differentiate v with respect to t. You see dv dt as your answer. Dv dt equals to, this one is a constant, pi r squared is a constant. We take it out, leave it alone, pi r squared. Differentiate h to the power of 1 with respect to time. You get dh dt. Okay, now it's just a matter of plugging in and simplifying, and so solve for what you are looking for. You are looking for dh dt, right? Let's do that. Dv dt is positive 3. You can put the units, but in mathematics, there's no need for you to put the units. They don't care really. They just want you the final answer, and then you know the units of the final answer. Those ones they will be looking for. Here we can just plug 3. If you plug in the units here, you will see they will cancel out. Okay, let's plug in the units, by the way, just to have to so that you get what's happening here. dv dt is 3 meters cubed per minute. Okay, we have pi r squared is 5 meters. They give us 5 there on top, 5 meters. It's here. Okay, so we are using that 5 meters as our radius. They said it's our radius, so we put it here. We have 5 meters squared dh dt. Okay, we use small letter h here. I've been using small letter h. So the answer for dh dt is going to be what? It's going to be these guys divided by these guys here. Okay, we have meters squared cancelling 2 of the m's here. Okay, meters squared there cancels 2 of the m's there. If we divide by m squared both sides, right? So your answer is going to be in meters. From here, meters there, you have meters there, and then you have what? Per minute. Meters per minute. Minute is here. That's going to be your answer. Meter, that is left here, and per minute, that is left here. It has nothing that is cancelling it. So you write there meter per minute. That's how that's what I mean by the units are going to cancel as well. And we are looking at the rate at which height is changing with respect to time. It should be in meters. Height is measured in meters. So the rate at which is changing is meters per minute. Okay. The answer here is 3 over 3 over 5 pi, not 5 pi, 25 pi, because you have 5 squared multiplied by pi is 25 pi. We divide by 25 pi both sides as well. We get 3 over 25 pi meters per minute. I hope that one is clear. Let's look at number 8. Number 8 here says the area of a triangle with side lengths A, B, and a contained angle theta is given by this one. We know this one from grade 12, that area of a triangle is given by 1 over 2 AB sine of theta for this triangle. This triangle has angle theta there. It has a side A and side B there. Its area is given by this formula here. Okay, so we have A and B, side A and B, and theta is contained by A and B. Theta must be between A and B, and that's when you will use this formula. Okay, now this is they give you. Now they say for alphabet A is given by B by 3 centimeters, and theta increases at the rate of 0.2 radians per minute. So we write here, we can write somewhere here, maybe here, that our d theta d theta dt. D theta dt is the same as what? D theta dt is the same as 1 over 5. I'm writing 1 over 5. I'm avoiding decimals. I don't want to work with decimals. If I work with fractions alone, that will be fine. Radians here, rad per minute. This is the unit for, theta. This is the unit for time. That is why it's d theta dt. Okay? The rate at which theta is changing with respect to time, radians per minute. I hope that one is clear. How fast is the area when theta is this much? Pi over 3. We are looking for how fast is the area increasing. That is dA. We are looking for dA dt. What are you expecting the units to be? We are expecting the units to be, I'm going to write them here in the brackets. They are going to be in meters squared. Area is in meters squared. Since we are, not meters squared, we are giving here the units that are given for A and B are centimeters. So we are looking for centimeters squared. Centimeters squared per minute. We are looking for these units at the final answer. Now here we are going to do what? We are going to take the derivative, time derivative, d over dt. For a is a to the power of 1. Differentiate it with respect to time, you get dA dt. Okay? Half is a constant. For a, they just said here for this triangle, a and b, they are going to be constants. Why are they being constants? For this, a is this much, b is this much, and then how fast is they say here, and theta is increasing at the rate of this much, 0.2 radians per minute. How fast is the area increasing? Now a and b are going to be constant in that, because they didn't say a is changing at this rate and b is changing at this rate. They just theta. By the way, if you look at theta here, if theta was this small, if this theta was this small, and then you have your side A and B, and then your theta here keeps on increasing, it has nothing to do with A and B. A and B will remain A and B, but this one will be changing. The area will be changing as theta, because the area here is small. The area there is much bigger. The area there is much bigger, right? That's what happens here. So A and B are constants, but theta is changing, and that's the thing, that's the variable that is changing the area. And now we are looking for how much is the area changing with respect to that time. So we have here a and b as constants. I see them as constant, as some real numbers, 3 or 2. There are 3 and 2 here, by the way. So you just leave them out. They have got nothing to do with this derivative of d over dt. Even if you use the product rule for these ones, because they are constant, you're gonna get dA dt and dB dt somewhere. Now those dA dt and dB dt, because they are zeros, because the rate at which a is changing with respect to time is 0, because a is not changing, is going to make those ones 0, because we're going to have a product of 3. There is a C of this problem where you differentiate and then all of them are changing. Now they are not zeros, they are going to be those values. We'll see with number with alphabet B how it works. But here, let's just continue with A and B as constants. For alphabet A and B as constant, we have 1 over 2. Put A, put B, and then differentiate this guy, sine of theta, because theta is the one that is changing. When you differentiate sine of theta, you get cos of theta. And what are you doing here? You're differentiating theta with respect to time. You must indicate next to it. Now, this is how we differentiate. Differentiate theta, and then you indicate you are differentiating theta with respect to time. If there was a time somewhere here, differentiating time with respect to time is dt over dt is 1. I don't need to write that one down. Okay, but here, this is what we get as our answer. From here, all we have to do now is to find this guy here, our dA dt. Okay, how do we find him? We just plug everything in. Everything is given there on the statement of this one, part A. Okay, just have to put everything in and find that our dA dt is the same as 1 over 2. We put A as 2. Like I said, putting in the units doesn't matter. You can just put the final unit that you know that is going to be meters squared per centimeters squared, because we're given centimeters this one. So centimeters squared for A per time is minute. Okay, so you just put half. A is 2, B is 3, and then you put cos of what? Pi over 3, and you close the bracket, and then you multiply this with d theta dt, that is just 1 over 5. Okay, and then the units for everything is what we just discussed them. It's centimeters squared per minute. Okay, and then we write we just simplify this now. 2 cancels with 2. You have 3 over 5. 3 multiplied by 1 over 5 is 3 over 5. Okay, so you put 3 over 5. Cos of pi over 3. Please refer to this video. Okay, I'm gonna keep on referring to this video for part B as well. That's how you find trigonometric values of simple angles like this, like pi over 3, pi over 2, pi over 4, all of those ones. Okay, now cos of pi over 3, according to that video, you will see that is what is just 1 over 2. Okay, so just write 1 over 2 here like this, and then you put centimeters squared per minute, and then you are done. Okay, you can simplify this and write it as this is the same as, I'm gonna put it here, is the same as 3 over 10 centimeters squared per minute. Okay, centimeters squared per minute. Now this is how you do it if A and B are constants. Look at B, part B of this problem of number 8. B is increasing. You see, they say B is now increasing. This time around now, B is no longer a constant. Okay, so we're going to do what? We're going to consider B and theta, both of them as variables. See, they say A is 2, B is increasing at this rate. So we're gonna have to write here that our dB dB dt is the same as that rate that they're giving us, 1.5 centimeters per minute. That is just 3 over 2 centimeters per minute. We can write it here like that. Okay, and then theta increases at 0.2. This is the rate of theta. It's still 1 over 5, 0.2. Okay, and then how fast is the area increasing when B is, and we apply the same thing. We apply the formula for the area. We use it, we differentiate with respect to time, but now the answer is not going to be this. The answer is not going to be this one. Okay, let's look at what's the answer now, this time around. Please write this one down. Write it down, and then we're going to compare it with what we are going to replace it with here, so that you can understand what's happening when what is constant, when what is not a constant. How do you deal with it? Okay, so we have here the derivative of A with respect to time is just dA dt. Put like that, and then half is a constant. Take it out, it has nothing to do with this derivative. A is also a constant. They didn't mention anything about A increasing or decreasing, so it's also a constant. You put it here, A, and then you differentiate now this ones, B and sine theta, with respect to time. You're going to deal with them as a product because they are a product here. So you're going to apply a product rule. So differentiate B with respect to time. Let sine take break. Okay, differentiate B with respect to time, you get 1 dB dt. So I'm going to open a bracket here and write dB dt sine of theta plus, now I leave B alone to take break. I differentiate sine of theta, I get cos of theta. D theta dt, I differentiate theta here with respect to time. This side I was differentiating b with respect to time. This side I'm differentiating theta with respect to time. Okay, and now we can just plug everything in and find the final answer. Now we will have here 1 over 2. A is 2. And then here you have what? This is just 1. Here we have what? dB dt they gave you there is 3 over 2. Sine of pi over 3. Theta is pi over 3. Pi over 3. And then you have what? Plus. B is what? Your B is given by 3. You put 3 there. Cos of pi over 3. Okay? You put it there. D theta dt is here. It's 1 over 5. You put 1 over 5 there. And then you close. But we have the answer for this one from the previous one. 3 cos of this, we know what's the answer. But we can just continue simplifying. The units here are still centimeters squared per minute. Okay? And then we can just proceed and simplify. dA dt is going to be 3 over 2. Sine of pi over 3. According to that video again that I referred to earlier, you're going to have sine of pi over 3. You're going to get it as root 3 over 2, like this, plus 3 over 5 multiplied by cos of pi over 3. We saw it was 1 over 2. We put like this, and then we write the units that are centimeters squared per minute. And then what's the final answer? Not necessarily the final answer. We're gonna still have to simplify. This one, 3 times root 3 is 3 root 3 over 4. 2 times 2, 4. And then we have plus 3 over 10, right? And the units here. I'm going to just make space so that we can proceed to the final answer. The units are still centimeters squared per minute. And then what we have here at the bottom, we have the denominator as 20, the lowest number that both 10 and 4 goes into, and leave nothing is 20. So 4 goes into 25 times. 5 times 3 is 15, root of 3. Okay, 10 goes here twice. 2 times 3 is 6. So you have there, this one is the final answer. Centimeters squared per minute. We can take out the common factor, but if a common factor here is just highest common factor on top is just 3. If you take that 3 out, it's not going to do anything special with this our 20. So we can just leave this as the final answer. It's like this. We are done. Okay, please don't forget to like this video, share and comment about the topic of mathematics that you'd like to see me covering next. Don't forget to subscribe as well if you want more videos like this. Bye.